Excellent. Hi everyone. We're a couple of minutes off from starting, but I just thought I'd open the meeting so everyone can start to come in. Because of the way we've set up this meeting, you're all on silence and you all have your cameras switched off. It just helps us keep the bandwidth for the meeting. We'll start just after 1:30. We want to make sure we maximise the time, but just to allow everyone opportunity to join. And as you see here, we have our two representatives from Fuel Cell Systems here ready to present to you today. So we're very excited about today's meeting. So we'll just give everyone a few more minutes to join, and then we'll start. But please be aware we're already recording. So yeah, just for your awareness, I'll do a few briefing notes just as we start around 1:30. So yep, just hold tight, gentlemen, and then we'll start just around 1:30. Thank you everyone for joining. There are quite a few people on the meeting now. We're just going to start in a minute or two. Just wait till we're just after 1:30 just to allow everyone the opportunity to join. Right, okay, so we're just at 12:30, certainly UK time. I guess we might have some overseas people. Thank you everyone for joining us today for the Hydrogen Energy Association's Hydrogen Byte session. I'm really pleased and excited to have our representatives from Fuel Cell Systems joining us today. In terms of the sort of just a few housekeeping notes for this meeting. So I'm going to start just by doing a very brief overview of the Hydrogen Energy Association for anyone that's not familiar with us. And then I will hand over to our two speakers who can introduce themselves, and then they'll go through their presentation. In terms of the setup, as you see, we've set it up in such a way that your cameras and microphones are automatically switched off. It just helps us protect the bandwidth for this meeting. The meeting will be recorded and will be available for download on our website, and that will be circulated after the meeting. We do encourage you to raise questions. There's a Q&A box at the top of the screen. There is a chat box if you're more familiar with that, but just for simplicity, if possible, please use the Q&A box. And as we come to the end of the presentation, I will go through the questions and encourage our speakers to respond to them. If we run out of time, we will share, as part of your registration, you allowed us to share your contact details with the speakers. So we'll share them. And if there's any discussions that need to take place offline after the meeting, then we will we'll do it in that way. So I'm just going to very briefly share my screen just for 1 second, just to give a general overview of the Hydrogen Energy Association. And Tom, maybe you can just confirm that you can see my screen.
Yeah, no, I can see that fine.
Perfect. That's great. Thank you. So this just gives you an overview of the membership we have. The HEA has been a trusted voice in the hydrogen sector for the UK for more than 15 years. We're a not-for-profit company that's driven to support our members within the hydrogen sector and to be a trusted voice into government on matters related to policy and barriers and then opportunities for developing hydrogen within our clean energy sector. Our membership, as you see here, spans from hydrogen producers, those involved in transportation and storage, and those involved in the utilisation, including fueling, and that's what we're going to be focusing on today. If you do have any questions regarding the HEA, our membership options and our activities, then feel free to reach out to me. You can contact me by email or you can find me on LinkedIn. So that's my very brief introduction. I've gone over the housekeeping. So I'm going to hand over to the Fuel Cell Systems team. I'm going to unshare and then you should be able to share, gentlemen.
Yeah,
I'm just going to make sure that's working, and then I'm going to switch my camera and mic off and hand over to you. I'll come back for the questions. So do remember to use the Q&A function, everyone. Thank you.
Brilliant. Thanks, Emma. Thanks for everybody for joining this Hydrogen Byte session. I'm Tom Chicken. I'm the CTO and co-founder of the company, and I've got my colleague Sam.
I'm Sam Whitworth, and I'm the engineering director for Fuel Cell Systems.
And we're going to cover a bit about hydrogen refueling. I can't see myself. There we go. I like to be able to see myself. Not much of a benefit, I think. So we're going to do a bit of a cover of hydrogen refueling, how it works, what it means for vehicles and the standards, and how it fits in with fuel cell systems and our product line. So I'll start off and I'll do a bit of a background of the company and sort of where we come from, where we are at the moment. So some of you may already know Fuel Cell Systems and myself. I've been around the industry for quite some time. I co-founded Fuel Cell Systems back in 2010, initially as a hydrogen fuel cell and hydrogen company, but it was quickly became apparent back 2015 that there's a big gap in the market for hydrogen refueling. There was a lot of vehicles coming online at that time, and there wasn't the infrastructure or the scale of products required to get that equipment with those vehicles refueled. So Fuel Cell Systems started developing a line of refueling equipment. If I click on the slides here, there we go.
Yeah, you're in.
And what became our early set of products is the HyCube. Those involved in the industry probably have come across a HyCube. Behind most demonstration projects in the UK, be it aeroplanes, trucks, cars, buses, there's normally a HyCube sat in the background doing the hydrogen refueling. And the HyCube is primarily a system for dispensing small amounts of hydrogen. So depending on the pressure, which we'll come to later, you can do about up to 100 kilograms a day with one of the HyCubes. But generally, they're used for low-scale deployments, such as a few cars, a couple of buses, things which demonstrate hydrogen within industry. And this is the setup we've got up at Toyota. We're quite proud of this one here. So you can see the HyCube on the left-hand side. This is the dispensing and the compressions part of it. And then we're also generating hydrogen on site in our electrolyzer container and storing it at high pressure. And this is a general setup of a hydrogen filling station, and in fact, almost any hydrogen filling stations.
I mean, that HyCube as well, I think the versatility of Toyota That thing's refueled buses, forklift trucks, cars, the new Hilux prototype. So one of the lovely things about that setup, as well as the layout and the setup, is actually the amount of data and insight gained from the number of different platforms that it's been able to service, which is.
Yeah, and it's been installed now for a couple of years, and it's one of these we don't actually hear much about it, but that's great. I was actually up there yesterday doing a few little work bits of jobs on our remote monitoring package, and there's a couple of cars that literally just driven off having just refueled, and the site's there just in use continuously filling up cars, and we don't hear about it because it's generally working. That's what we want. We've been doing this for quite some years now, primarily with the high Qs, but we've also got the refueling truck, which a few of you may have seen on top right-hand corner. So as Sam said, we've been filling up Hilux here. I'm pointing at my screen like you can see, but you got we've got Hilux here. We filled up the BMW prototypes. We've got the first hydrogen van. Actually, there's the handlings.
Extra airport.
That's the one.
The ground handling equipment. You were at Goodwood last summer with the Rally Hilux. The Rally Yaris, and that was 700 bars. That was an experimental refueling protocol. So yeah, the diversity of the range has kept growing.
And actually, that's a good point. So in hydrogen vehicles, the gas is stored in a compressed hydrogen tank within the vehicle, and there's generally two pressures that's stored at. It's either 350 bar or it's 700 bar. And they both got their pros and cons. Generally, a 700 bar vehicle, you can get more gas into a smaller amount of space. However, it uses a lot more energy to get that gas up to 700 bar. 350 bar needs a larger volume, but it is less energy. And generally, what we see at the moment is large vehicles or heavy transport, such as the buses in the middle there, or the aeroplanes, actually were all stored at 350 bar because they had the space in order to accommodate the tanks. The vehicles, so the Hilux, the cars there you see, are all stored at 700 bar because they don't have the space for the tanks. What we're actually going to start, what we're seeing now is that the 700 bar is scaling up into the larger vehicles. So
these now are looking 700 bar where they weren't previously.
Exactly that, so they can fit more gas into the same footprint as 350 bar, and they're willing to take that payoff on the energy because they want to have fewer refuelings between stops. So that's the overview of the vehicles. Then moving back into the hydrogen refueling. So as I said, you've got a compressed gas tank within the vehicle, and you need to get gas into that. And it's not like a petrol pump where you can just drip the liquid into the tank. You have to use pressure differential generally to get the gas in. So one of my old colleagues always explained it like getting two balloons. Your one balloon is empty and that's your car, and you blow up another balloon really full, and that's your hydrogen storage on your hydrogen refueling station. And if you tie the two ends of the balloon together, the air from one balloon will fill to the other one and they'll balance up. And that's exactly what we're doing for hydrogen refueling. You need that higher pressure to get the gas into the lower pressure tank. And there's three main ways of doing that. I'm generally talking about gaseous hydrogen, not liquid. That's probably a whole separate hydrogen byte session. Decant method is the most simple form of refueling, and that's where you get one large tank, and that might be a tube trailer or just a large storage bank, and you do that. It's exactly like having one large balloon and a small balloon, and the gas will flow from one to the other. And that's great. It's simple, it's easy to control, but you can't get the most gas out of your one tank. You're wasting over 50% of the gas in that because you haven't got that headroom. As soon as you start using the gas from there, the pressure drops and you no longer have that big pressure delta between storage and vehicle.
And at best, they'll equalise. You'll only ever flow downhill. So at best, they'll equalise, and that would be the end of that refueling.
Exactly. So then the way that most stations operate is actually on the cascade method. And that's rather having one single tank, you have multiple, and that might be 3, 4, 5, potentially even 10 various different tanks, either the same pressure or different pressures. And when you bring your vehicle along, you always start with the lowest pressure tank first, and you equalize that pressure. And then you get your next one and you equalize that, and you work your way up. And so eventually you've got a full tank, but you've maximized the amount of gas from your cascade. And that means you can store different pressures, means you can optimize your energy levels to get the gas to the right pressure that you need. You're not wasting gas that you've generated at quite high cost in order to get the pressure in. So the cascade generally is the way that most filling stations operate. Then the final way you can do it, and we have done in the past, is direct compress. That's where you take your hydrogen storage and you run it through a compressor, and that will take the gas from whatever pressure it is and compress it up to the 700 bar, 350 bar in your vehicle. It's got some benefits. It means you don't have to have such a large intermediate storage. You're not compressing all the time. However, compression generally takes a lot longer. And if you want to keep it at the same speed as the cascade or the decant, you need to have a very large compressor, which is the capex cost that's become considerably high, plus the opex of actually keep running at that level for a short period of time. So those are the three main methods of filling. Then the question people often ask is about cooling. People have heard about different cooling methods within hydrogen refueling stations. So I've apologies for the boring slide here, but I thought it was important to just sort of lay them out all nice and simply. Hydrogen is a funny gas. There's only two gases. Hydrogen and helium behave differently. So if you push compressed air through a small orifice and it lets it expand, it will get cold. However, if you put hydrogen through a small orifice and let it expand, it gets hot. That's not so much a problem, except also when if you have an empty hydrogen tank and you recompressing that gas in there from 50 bar up to 700 bar, you've got an adiabatic compression heat element as well. So you've got heat coming into the tank and the tank itself are getting hot. Again, that's okay, except the tank should not exceed 85 degrees in the vehicles.
It's probably worth just saying that this is talking about hydrogen for transport as well. So generally we're talking about type 4 tanks, which are composites. So the makeup of those tanks with the resins in them, there's a thermal cycle they don't want to see. That isn't the case maybe with some of the type 1 tanks where they're predominantly made of steel and the temperature cycle isn't so much of an issue. But when you're trying to take the weight out and use hydrogen for transport applications, this thermal cycle potentially could be quite a big issue, which is why taking the heat cycles out and therefore cooling the gas is so important.
Absolutely. And then and because we are talking about sort of public refueling stations where any vehicle could rock up and fill up, you've got to allow for the worst case. So we've got to allow for a type 4 tank, which is well insulated, not able to dissipate the heat quickly. And the way we do that is we follow the protocol of J2601. J2601 is kind of the Bible of refueling. It tells you how you need to comply in order to fill up vehicles safely, so that if any hydrogen vehicle is designed to the right standards, we know that we can refuel it. And that takes into account various different elements, including sort of pressure, ramp rate, ambient temperature, but also hydrogen cooling. So the way that we allow for fast refueling and not exceeding that 85 degree sort of figure is to pre-cool the hydrogen going into the tank. And that can be done at various different temperature levels. It can be done at T20, which is minus 20 degrees chilling, all the way through to T40. And what we often get when people ask us about refueling is immediately they say they want 700 bar, minus 40 degree filling as fast as possible. And that's where we often need to step in and say, are you sure? That's probably what I'm going to hand over to Sam.
Yeah, I was going to just touch a little bit more on refueling protocols and what they mean in the real world, because I think anybody in the industry will have heard various flow rates. The current flow rates typically in J2601 are up to 60 grams a second. So that's every second 60 grams of hydrogen is being transferred into the vehicle. But actually, that's not what's going on in J2601. What's going on is a regulation of the pressure ramp rate, so that the how many megapascals per minute can the tank's pressure being increased by. And what that ramp rate's doing is limiting the rate of compression, so that secondary heat cycle. And J2601 looks to balance the ambient temperature conditions. So how warm a day is it? You can put the gas in quicker at a 10 degree ambient condition than you can up at 50 degrees, which is the limit at which you stop refueling. So J2601 is balancing the ambient temperature, the pressure ramp rate, and also the temperature of the gas going into the tank. And it's a combination of those three things that sets the flow rate. So the flow rate into the tank is a function of the tank size, because a larger tank needs a higher flow rate in order to maintain that pressure ramp rate. So we talk a lot about flow rates, but actually it's the governing temperatures and the pressure ramp rates which are setting the scene really to set those flow rates. In terms of those protocols, just to give you a little bit of an insight, the J261 protocol covers 350 bar refueling up to tank size of 250 litres or 6 kilograms, and then all of the 700 bar refueling. And then there are a few subdivisions. So if you're looking at, say, for example, forklift trucks, that would use a -3 protocol. That's a very simple system where the flow rate is restricted by a fixed area, so an orifice plate. And then you get onto some of the higher capacity refueling setups. So J261-2 deals with tank sizes above 6 kilograms for 350 bar refueling. And then the sort of TIR protocol that's just been released and they're awaiting feedback on is the -5 protocol. And that is for flow rates up to 300 grams a second and from tank sizes from 250 litres up to 7,500 litres. And I've just sort of thrown a load of data at you there. And what does that mean? So if we just move on to the next slide, I'm just going to talk around what that actually means. So if you look at this graph here, this graph is displaying 8 different sets of data. Interestingly, you'll see 7 lines there, and that's because a 20-degree ambient T40 and a 40-degree ambient T20, the delta T is the same, so the lines marry up perfectly. So you only see 7 lines of the 8 because one's overlaid. But what does this mean? What this means is it has a direct effect on the amount of power, the amount of cooling power your refueling site is going to consume. And the cooling power is directly proportional. So if you double your flow rates, you are doubling the cooling power you need in your site. So if you want to refuel at 300 grams a second, and you want to do that on a 50-degree ambient day right at the limit at a T40 protocol, you're going to be consuming over 400 kilowatts of cooling power. And that's without the efficiency. So by the time that becomes the real world, that's probably north of 450 kilowatts. Whereas if you can refuel, let's say 120 grams a second, and you can do that on the T20 protocol, you'd be limiting your cooling power to 100 to 150 kilowatts. Just to put that in perspective, what does that mean? If you looked at, say, a 50 kilogram tank, so a large HGV, 50 kilograms of hydrogen being transferred. If you were to transfer that at 300 grams a second, your refueling time, brilliant, 3 minutes, but you're looking at 400 plus kilowatts of cooling power. If you were to slow that down to 120 grams a second, you're talking about 7 minutes of refueling time. And if you were to reduce that further to 60 grams a second, you're talking of 14 minutes. When you come down to 14 minutes and 60 grams a second, you're getting that cooling demand down to around 50 kilowatts. And that's one of the key things we want to get across today is it's not just the capability of the system, it's the impact of deploying it. And are you able to get a grid connection for 0.5 megawatt? Or do you size your plant and your system to work with the grid connections that are available, and also to manage that operational cost? You're paying for that energy you're using to cool that gas. So anything you can do to drive efficiency through the protocols is absolutely key to unlocking deployments. If we just move on to one more slide. So what we have here is a high fleet base station. So high fleet really is our bigger version of a high cube. And this station we have on the screen here has been developed for our partner at Byte Mobility that we're deploying in 2026. And this station here has a capacity in excess of 3 tons a day dispensing. So what you can see here is all the fundamentals you need to build a hydrogen refueling station. I'm just going to touch on them quickly and then make sure we hand the floor over for some Q&A. So any refueling station needs these 5 building blocks. The first thing you need is a source of hydrogen. You need to put the gas into the system. In this example, it's coming from the tube trailer, but actually that could come from on-site electrolysis. The big difference really being with electrolysis, you're generally getting a much lower output pressure, so you've got more compression to do, whereas some of the tube trailers now, they're getting up to sort of 350 bar plus, so you're getting a lot more stored energy delivered to site, which can help with the site throughput. You need to compress the gas. So you can see sort of 2 boxes with the green lids. That's our high fleet system. High fleet is a self-contained control system, gas management, compression and dispensing control system. So all of the smarts within a refueling station are contained within that box. And really our value add to the world is we do that all in the factory. So instead of sort of going to site and doing all that site integration outdoors in the mud and the rain, we're doing that here in the factory, and it becomes a plug and play exercise to configure your site. That's how we're trying to tackle this problem. Once you've compressed the gas, you need to store it. And we typically store gas at 2 pressures. We store gas at 500 bar and 1,000 bar. The fact that the 500 bar is there for 350 bar refueling, And for 700 bar refueling, just to use the cascade method that Tom was talking about earlier, we use the 500 bar and the 1000 bar, and we work our way up the hierarchy, and that drives efficiency.
I think it's and with that storage as well, you might be coming to say we subdivide that storage into multiple banks for the cascade to optimize the amount of gas we can get out of it to increase efficiency further. So Pipely by standard has 4 inputs, but each of those can actually be doubled up and tripled up to get more cascade inputs in order to improve the efficiency.
Absolutely right. Yeah, absolutely right. The cascade's really within reason equal efficiency. There's obviously a limit, but the equal efficiency. And then you need to dispense the hydrogen. So you can see 4 of the high flow dispensers with a couple of heavy goods vehicles pulled up to them, and those high flow dispensers are paired with our high chilled chillers, and that is how you get the gas. So they are an integrated dispenser. They can offer 350 bar or 700 bar or both in one system with an integrated liquid-based heat exchanger, and there's a coolant line running to them. And we pair the chiller and the high flow to maximize the throughput while minimizing your energy demand. And that's really one of our key points, is our focus is minimizing the operational cost by maximizing the efficiency. So anything we can do to reduce the cooling energy, the amount of compression, the compression energy, to make your sites more efficient, that directly equates to taking the cost of the kilo of hydrogen when you're dispensing it. Anything we can do to drop that kilogram price should be our headline focus in this industry. I think it probably makes sense to pause there and make sure we leave a healthy amount of time for any questions that may be coming.
Yeah, I think you're right.
Thank you so much, Sam and Tom. I really appreciate it. We've had, as I expect, a lot of people on this call. We have more than 100 people sitting here, I think, absorbing all of this great information that you've shared. So really, thank you very much. We have a couple of questions in the Q&A. A few more minutes left. I guess I'll just start perhaps with a couple of questions myself. One of them, I mean, you've talked about, I guess, the technical and the infrastructure aspects, but I guess if we look at the big picture and the policy landscape for hydrogen transport and hydrogen refueling, what do you feel are some of the barriers to preventing, or what do we need to enable, I guess, this rollout of hydrogen transport and fueling systems? What are your asks, let's say?
I suppose at that level, we always come back to the slight chicken and egg conundrum of what's going to come first. Is it going to be off takers, or is it going to be the ability to dispense hydrogen? And for us, we feel it has to be the ability to dispense. You know, that there has to be that investment made in a network that allows people to take those vehicles and to start using them reliably. So I think we need to get that critical mass of stations out there, and I think that comes with effective deployment of some of the funds out there. So whether that is UKRI, whether it's DFT or the other platforms available, but making the most of that support that's available to the industry and using it to get systems built, I think is one of the key things we can do.
Okay, so policy support to enable just the rollout of infrastructure to get these vehicles moving on hydrogen. That's, I guess, what I'm hearing there. Thank you. And you've talked a lot about some of the technical aspects and why you might choose one system or protocol over another. Is there anything that you'd like to expand in terms of these technical barriers that the average user of a hydrogen vehicle might encounter?
I think for the user, I think the stations are very intuitive, and they are so similar to conventional refueling with, say, diesel or petrol, that it really is plug the hose in, press go, and it will tell you when it's done. In terms of getting the sites out there, I think the key technical barrier for me is all about energy usage. Anything we can do so that we don't need grid connections. I think anytime you're going to go to the DNO and ask for 0.5 megawatt, you've probably at the moment, unfortunately, got quite a long wait on your hands. Yeah. So what can we do to think smart and to use much less energy, do things slightly differently, take a slightly different approach so that we can operate within the grid constraints we have. And I think that's one of the key potential benefits of hydrogen. You know, but there's so much debate around, should we electrify, should we move to hydrogen? And our answer is do both. There's some brilliant applications when electricity doesn't work, look to use hydrogen, but do it in a way where you don't need to go and get 0.5 megawatt. Because if you're doing that, you know, maybe you're not delivering the benefit that you otherwise could be.
Sure. So limiting and making as efficient as possible the energy associated with the dispensing. That's great. Thank you. I'm going to move into the Q&A section. Thank you for those that have added a question there. So Michael Oxley has said, you say vessel types and vehicles tend to be type 4. What type are the on-site storage cascades in the station itself?
Okay, so generally we stick to type 1 storage on site, type 1 being standard steel cylinders. And the reason for that is because on static stations, we're not too worried about the weight saving, which is where you get the benefit from the composites. And the cost for manufacture is lower than the composite side of that's there. So generally type 1 or type 2 is the on-site storage.
Thank you so much. Eduardo, sorry, my name here. Eduardo Brails has asked, have you considered ammonia to hydrogen or methanol to hydrogen reforming systems to reduce overall storage volume? So are you looking at any derivatives associated with your systems?
I think the short answer is no. And the reason for that really is we want to operate within the standard protocols for refueling, but also the standard protocols for fuel quality. So any refueling station needs to be able to dispense hydrogen of the right quality to get into a fuel cell. So we don't want to be doing that processing on site. We want to be taking certified hydrogen of the right purity and putting it through the system. I think all of those, certainly if you look at transporting hydrogen greater distances, whether that's production where there's lots of sun in the Middle East or in the north of Africa, then I think ammonia has an enormous use case. But I think that's upstream of the end dispensing point. Yeah.
It's a great answer. Thank you. I'm going to rattle through these in the time we have. It's quite a few. So Will Forshore has said, what type of compressors are you typically offering in your systems?
That's a really good question. So where we're trying to generate the very high end pressures, we're using hydraulic boosters. So that is effectively where you have a hydraulic power unit, an electric drive motor supplying hydraulic pressure. That pressure goes into a hydraulic cylinder, and that is what's stroking the booster cylinder. So we use dry lubricated boosters, so there's no oils or contaminants, so we keep the hydrogen purity, but it's a hydraulic actuating cylinder. That's what we need to generate the high end pressures because we're going to 900 bar plus. There are some great applications where we're looking at diaphragm reciprocating compressors. In the lower pressure applications, you get a bit more efficiency and a bit more throughput from those, but they won't drive the end pressure. So we typically see a switch over and that we go to those hydraulic boosters when we're looking at the high end pressures.
Okay, thank you so much. Albert Cott says, thank you for a very good presentation. So well received. He said, I have a question regarding the connection between the tube trailer and the hydrogen refueling station. How do you identify the pressure, temperature, volume, or other relevant data from the tube trailer, assuming that, so I'm just going to get to the end of the thread, assuming that tube trailers are from different suppliers?
Yes, it's a very insightful question. There is a standard over the tube trailer hose in terms of the mechanical interface, and you'd catch me out on quoting the right SAE number, but there's a standard on the refueling hose between the tube trailer and the panel, and that takes care of the mechanical interface. So you can connect multiple different tube trailers from different manufacturers or suppliers into your intake panel. What happens in the intake panel? So one of the first, I guess, products that we put into a site is this intake panel, and when you make that connection, that is reading the pressure and the temperature of the gas coming from the tube trailer. And that goes into the control system, and we use that to determine what's happening before we open any of the valves. We actually have to go one step further. So some of the tube trailer manufacturers will require pilot air to open the valves because they won't want an operator to be near the tube trailer when that flexible line is first pressurized for safety reasons. And again, the system's able to provide the pilot air to do a leak detection and pressure check on that line, and then to open up the system as it goes through the levels of checks on the availability and safety of the system. So it's really just through control. The fixed system is rated to much higher pressure than the tube trailers. The tube trailers at the moment generally are topping out at 380 bar. Everything in the site is rated up to 1,000 bar. So that's in our safety hierarchy because we're feeding a lower pressure into a higher pressure. So we're able to open it up to read that pressure and then to move on if it ticks the correct boxes.
Yeah, that's great. Thank you. Michael Oxley has come back with another question. So he said, now I'm going to read this very carefully to make sure I've got it right. He said, 300 grams per second minus 40 degrees C consumes a lot of energy, I would assume. Is this done with a single chiller? It must be quite large.
Yeah, it's a really insightful question. And you get to a tipping point. So with chillers, there are a couple of things that drive the size, the energy demand, and ultimately the cost point. So the first one is the end temperature. So if you're trying to chill something down to maybe 0 degrees, you get quite a decent coefficient of performance. You can get more. You can take energy from the environment. So it's not all being covered in electrical energy. As soon as you start dropping, the environment can't do anything for you. So at best, you're going to get 1-to-1 1 unit of heat energy out for each unit of electricity you put in. But in reality, with some losses, you won't achieve that. So the lower the end pressure, the more energy you need, for 2 reasons. One, you're taking the gas down further, but 2, the environment can't really do anything for you. In fact, it becomes a hindrance. The second point is, yes, there is a size. So generally 75 to 100 kilowatts. And what you're doing is playing that game between how am I deploying my capital most effectively? So can I have 1 chiller? And when do I get to a tipping point where 2 chillers may be beneficial? And there's a couple of reasons 2 chillers or 3 chillers would be beneficial. One is the resilience of the system. So if you had a problem with one, you have redundancy or resilience in your system. The second one is actually operational efficiency. So you need to size your chillers to work on, you need to set your peak performance. So you might say, I want peak performance at 30 degrees ambient. And you accept that when you get to 40, 45, 50 degrees, you'll start to lose some of that cooling performance. So you have to go slower. But ultimately, when you go below 30 degrees, so say it's a 15 degree ambient day, or it's a bit less than that today, it's quite a chilly day, you won't need as much. You're able just to bring online the chillers you need. So there's some system efficiency there saying, I'm not going to bring on all 400 kilowatts. I'm only going to bring online the 200 that I need today. But I think the ultimate thing is to be realistic with your off-takers and say, what do you actually need? Do you need to refuel the bus in 4 minutes, or is 7 minutes perfectly appropriate? And that has quite a big effect on the bus depot guys, getting them maybe from 60 kilowatts down to 25, 30 kilowatts. And that's so anywhere where we can meet the operational requirements without putting in the huge plant is really where we start off.
And as well as the chiller as well, you've got to make sure you've sized your heat exchanger correctly to go alongside that. So we size our heat exchangers to currently in line with sort of 60 or 120 grams per second flow rates. As soon as you start stepping up to 300 grams, then you're also going to have a lot larger heat exchangers, which you probably won't be utilizing most of the time. So it's quite a large capital outlay for something you may not actually need.
Yeah, that's right.
Yeah. So trying to optimize the end use demand with the system design, I'm hearing. We're slightly over time, but I'm just going to take the opportunity, if I may, just to go through the rest of the questions, because they'll all be recorded, if that's fine for you. So Luca Alibardi from Cranfield University said, thanks for the presentation. Can you expand on the integration with an electrolyzer, and do you have a preferred type of electrolyzer?
Okay, so I think this came at the beginning of the HyFleet site. We talked about the source pressure and said, okay, you may have a tube trailer, you may have an electrolyzer. Typically, if you're using an electrolyzer, you're going to have an output pressure from the electrolyzer anywhere from 20 to 35, maybe up to 40 bar. That's the current range of technology. What that means is if you take a tube trailer, you might start off at 300 bar and you might finish at 30 bar. So although you finish at 30, your average pressure through the range is about 140 bar. So you've got a much higher source pressure. What that means is your compression rate is higher. So you're able to utilize the gas in the tube trailer. With an electrolyzer, it simply means you've got to do more work. So you've got to put more energy into the gas on site to get it from that starting point of 30 bar up to your end pressure. So that really is the key consideration when integrating with an electrolyzer. And typically you might find you use a pre-compressor, which is doing that first bit of compression, because there are more efficient ways to do it with the hydraulics we use in the higher pressure systems. In terms of any type of electrolyzer, no. As long as the output quality is appropriate for the application, really we can interface with any type of electrolyzer.
Oh, you're on mute there, Emma.
Nearly got a whole meeting without you.
Thank you so much. Schoolgirl error there. So sorry. A couple of questions on water. So what type of water quality is required for the cooling system? How does it work? And then the typical water demand. So I don't know if you can expand on those parts. So
the systems are all closed loop. So we use we'll use either a water glycol mix in a closed system, or we use a product called high cooled for the lower temperature applications. So to chill hydrogen down to minus 40, you've generally got coolant at between minus 45 and minus 50. So there's some additives in there to keep it as a liquid. It becomes pretty viscous, but it's still a liquid down at those temperatures. So they're closed systems. So there isn't an ongoing demand. So they're working really as refrigerators to cooling plants. So they're sending the temperature to the atmosphere. So there's fans on the top of them. So it's going through multiple phases of refrigeration within the cooling plant.
Okay. That's great. Thank you. Next question from Paula Blanco Sanchez. Are you aware of any leakages of hydrogen when transferring from the station to the vehicles? Do you have any devices to measure these leakages?
So the very first thing you do in J2601 is a leak test on the hose, basically. Now what happens is you send a pressure pulse to the vehicle, and that pressure pulse determines that the hose is connected correctly and that everything's leak tight before you start the refueling. So there's a pause where you measure the pressure. The way the receptacle works on the vehicle is there's basically a poppet valve, and the station pressure has to exceed the vehicle pressure in order to open the poppet. So it's not possible to open the valve without being properly connected. So we don't see cases where I think the question's coming from a place, say you have like a petrol hose and it isn't improperly, do you get splashback? Yeah. And the answer to that is no, because the hose has to be properly seated to open the refueling hose valve, and then the pressure has to exceed the vehicle pressure to open the poppet valve. So it's not, without a proper connection, it's not possible to open the valves. And then the leak detection is there. The hoses are replaced on a service and maintenance schedule based on a routine. But that leak detection is there to ensure that everything is leak tight before the main flow of gas begins.
Yeah, great. Okay, final question is from Jordan Cullen, who I think you probably know.
I recognise that name. Yeah.
Yes, it's a great presentation. From a deployment perspective, particularly considering the high cube, what considerations must be made by the customer at their site?
That's a really great question. And the answer is somewhat, it depends on the deployment. So if I go back to last time when we talked about doing Goodwood Festival of Speed, actually we were able to set that up in an afternoon for use at a festival. So the customer obligations were very little. If you want to do something much more permanent, so you want to put something in, there may be a small degree of civils involved to provide a concrete pad for the equipment to sit on. If you looked at the Toyota site Tom shared at the beginning of the presentation, there was open channeling so that the pipework could be just below the surface but open to the atmosphere, so it could vent, but there was no trip hazard. So deliberately, really very little. It's designed to be very fast to set up. It's designed to be something which you can relocate. I think the Exeter setup actually moved from Cranfield University to Exeter in a day and was set up and commissioned the next day. So they're designed to be rapidly relocatable for exactly that unit. But for the more permanent stuff, you can really a little bit of civil. So
and actually a lot of it is down to sort of risk assessments and site assessment surveys. So we follow the British Compressed Gas Association guidance on separation distances. So the high cube itself, it can just go on sort of half standard as long as it's suitable for the weight. But if it's next to a substation, then we probably want to look at moving that and sort of separate it. And if it's open to the public, we might want to put some temporary access control into all the limits of misuse of the system. So it's very site dependent, but as an absolute minimum, you can, as long as you've got power and sort of an earthing system, you're good to go.
Yeah, perfect. Okay, that comes to it. Thank you so much, everyone, for adding your questions. I think that's added a few more minutes, but certainly a lot of really good interaction. And Tom and Sam, I'd really like to thank you for this great presentation today. As mentioned, we'll be sharing certainly with the speakers your contact details. I'm assuming, gentlemen, we're fine to share your slides from today.
Yeah,
if you can
absolutely.
send them to me, then we'll do that. And for anyone that wants to watch all of this again or was not able, his colleagues not able to attend today, we will have this session available on demand on our website in the coming days, and we will communicate when that's ready. So thank you so much, everyone, for joining, and thank you very much to our speakers today. Really great presentation, and appreciate your time. Thank you.
Thanks for having us. Yeah,
thanks everyone for watching.